Here's some factorials. Let's just practice, make sure we've got this down. So 2 factorial just means 2 times 1. 4 factorial is just 4 times 3 times 2 times 1, which is, let's see, 6 times 4 is 24, or 12 times 2 is 24. If you don't like writing x's, it's a good time to stop doing that right now. So 13 factorial is obviously 13 times everything, whoops, smaller than that. And I'm not even going to write them all down because I have a calculator with a factorial button. So I'm just plugging it in and it produces an awesome answer, which is actually quite large. Okay, there you go, 6,227,020,800. Woo, that's pretty big. How about 0 factorial? Interesting, right? So if it's supposed to be the product of this number and all the positive integers smaller than this number, that doesn't really work for 0, does it? But 0 factorial is going to come up in our probability studies. We are going to run into this. So it needs a definition, and it has been defined. 0 factorial is 1. And you just need to memorize that and use it. Now, how many ways can 5 friends sit in a row? You know, like when you go to the movies with your friends and you try to decide who's going to sit by who. So we want to know what's 5 factorial. This one is actually so easy to just write down and figure out. It's probably faster than my calculator. So I'm just going to do it. 20 times 6 is 120. We are done. But remember your units, that is 120 ways. We need to answer that question, okay? Also, when you see word problems like this, I do expect to see this setup right here. I don't want to see a bunch of multiplication problems worked out on the side of your paper anymore. I really encourage you to use calculators for that kind of stuff or mental math, but I want to see the setup every time. So your work should look just like my work. Here's something kind of different. How many ways can I arrange 2 letters chosen from the alphabet? This is different because we are not rearranging the entire alphabet. What this means is if you could pick any 2 letters from the alphabet randomly, how many different arrangements of any 2 letters could you make from the alphabet? So we could start with the list strategy. Okay, obviously I could pick A, B. Those are 2 different arrangements, right? B, C, well that's possible, or C, B. And we could go on this way in my little list, but keep in mind that A, Z is also okay, and that means Z, A is another possibility, and let's see, this kind of starts to look like an infinite list. It's too long for the list strategy to be convenient, so I'm not going to do that. I'm going to use my slot strategy. We're picking 2 letters at a time. All right, now how many letters do I have to choose from? When I choose that first letter, there's 26 letters in the alphabet. I could choose any of them. Once one of them is locked in, I only have 25 letters to choose from for my second choice. That's still quite a bit. And then I stop. This is only 2 letters. That's it. So the calculation is 26 times 25. This is 650. I did it on my calculator, but I showed my setup. Okay, which is what I want to see. You don't need to list them out. The slot strategy is very efficient for small groups of things, so it's a great method. What about when things get bigger and bigger? It becomes less efficient to use slot method when you have a lot of slots. So there's a formula. And here it is. This is the permutation formula. It looks a little bit intimidating, but really it's exactly with the math we have already been doing. So let me show you how it works. If we use our previous example of 26 letters and choosing 2, what this looks like is permutations of 2 things from 26. Then you fill those numbers into the formula. So on the top we have 26 factorial, and on the bottom we have 26 minus 2 factorial. Let's break it down and see why the formula looks like this. So what we're calculating is all arrangements for 26 letters. In the denominator, we take 26 and we subtract the number of objects we're choosing. We're left with 24. 24 is the amount of spaces that don't exist. Since it's factorial, this is all arrangements for the letters not chosen. Well, let's see what it looks like numbers-wise. 26 times 25 times 24 times 23 times 22. and on and on and on. Okay, that's what the numerator is going to look like. The denominator is 24 factorial, right? 26 minus 2. So it's going to be 24 times everything smaller than 24. Think about how this works with fractions, on and on and on, all the way down to 1. Okay, look at what we can reduce. We've got all kinds of common factors, right? We can reduce those out, those, all the way down to 1. The only thing that will be left will be this. Does that look familiar? That's the same product we were looking for with the slot method. So you can see that the formula is really just a consistent way to churn out the same kind of results we got with the slot method. When it is useful is when the numbers get bigger. So as this number r grows, if it isn't just 2 slots, like I said, if you've got 10 slots or 11 slots, even 6 of them, you might not want to write that out and multiply it out that way. You can just plug things into this formula. If you're doing the work this way, this is the setup part right here. This needs to be shown before you say that it equals 650. Let's see what else we can find out. There's 2 ways I want you to think about doing permutations. The slot strategy is great if you don't have very many slots. As the numbers get bigger, as you're pulling larger sets and mixing them up in different arrangements, I suggest you use the formula. So those are 2 really powerful tools for calculating permutations and using factorial. All that's left now is to go practice. So it's your turn.